If you've been around the world of 3D for long enough, you've probably heard the term frustum culling before. For those who don't know what this is, frustum culling is, in short, an optimization technique involving not drawing things that aren't in front of the camera, and that's a little bit easier said than done. If you've ever heard someone make the claim that in video games, if you're not looking at something, it doesn't exist, a lot of the times that's what they're referring to. I'm personally not really a fan of people saying that because it oversimplifies a lot of things. But the point still stands that if you're able to only draw objects that are actually in view of the camera, it is possible to make your game run quite a bit better. So in GameMaker, I've said on a few occasions in the past that I don't really think frustum culling is actually all that good because GML is fairly slow in execution speed and, in a lot of cases, almost as expensive as just drawing the thing in the first place. Obviously, for drawing a lot of large models with a lot of vertex data, and then that won't necessarily be as true, but for something like this, by all accounts, even weak integrated GPUs from like 5, 6, 7, 8 years ago won't have that much trouble drawing a collection of trees, which are only a few hundred vertices each. Meanwhile, figuring out if each and every one of these several hundred tree objects are actually in front of the camera is a bit of a math-heavy job. Nevertheless, at some point semi-recently, I did realize that you can actually use the 3D collision hierarchies that I've been developing in this project for the past 2 years to significantly speed up the process of frustum culling, because if you have a bunch of objects sorted into a hierarchy like this, it then becomes possible to eliminate large chunks of the world at once, and instead of checking every single object if it's in front of the camera, all you have to do is check the camera against the collision hierarchy, and you can then figure out fairly quickly if a large number of objects are in view of the camera or not. It's still not quite a silver bullet when it comes to performance, but in some situations it can definitely help. So let's get on with it. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. Sort of, we're not actually going to be doing collision math today, so let's do it. So for those of you who don't know, a frustum is the shape of what you can see in the camera. For a perspective projection, like we're going to be using in our 3D games, for the most part, that shape is going to be basically a four-sided pyramid with the top lopped off. It's going to have 6 sides, the top, the bottom, left, right, and then the near and far clipping planes. And anything that is not inside that four-sided pyramid with the top lopped off will be considered not in view of the camera. For orthographic camera projections, where parallel lines don't converge at a distance, that shape is just going to be a rectangular prism instead. Just a tiny warning before we start, I have been notoriously bad about both spelling and pronouncing the word frustum correctly in my life. I'm just going to assume that I'm going to get it wrong at least a couple of times before we're finished here, so sorry in advance. So for frustum culling, I think I'm going to split this into 2 videos. First, we're going to set up the camera frustum. We're going to figure out like how to calculate that, and I'm also going to include a debug draw so that you can see it in the world. And in the next video, I'm actually going to do math with that camera frustum against objects and against collision hierarchies to figure out what is contained within it. I've realized that there's a decent chance that people are going to come across this video without having watched the rest of the 3D Collision series. I'm going to be proceeding with this under the assumption that everyone is on the same page about how this project is set up. If you are not, I'm not going to force you to watch all previous 30-something videos in the series before you watch this one, although I would definitely appreciate it if you did. But at the very least, look through the Github repository that's going to be linked in the video description and see how a bunch of the code relating to matrices and a bunch of the code relating to things like axis length bounding boxes and the various hierarchical data structures work, because frustum culling is going to depend on a few different things of that nature. So in the 3D Collision Test World project, I'm going to run this. I did a little bit of work off screen, and that's going to involve basically adding a secondary camera down here, which is going to be a bird's eye view, and then once we start doing actual frustum culling against the world, everything should still be visible that is within like the actual view of the main camera, but you will be able to see down here in the secondary camera that things that are not within that frustum are not actually going to be drawn. And I've also just added a little counter, which is going to tell us the number of things which have been drawn, the number of times vertex submit has been called on a tree. That number should obviously go down quite a bit if we're not going to be drawing things behind the camera. Also, I suppose while we're on the subject, take note of the FPS_real. Right now it's hovering at about 110. Hopefully that'll go up a fair amount by the time we're done here. So this time, I don't actually have to do too much initial setup and make too many changes to my existing 3D collisions project. There is one thing, however, which is that in the call plane constructor, the plane's normal is being normalized automatically once you pass it into the constructor. We want to get rid of that. If you're just doing 3D collisions against the plane, that's fine. But we're going to be doing a few other things with planes when it comes to constructing a camera frustum, and we're not going to want that there because that's going to mess with the values a little bit. Next, I'm going to go into the collision stuff folder, and I'm going to create myself a call camera frustum script file. This is going to be a constructor. This is going to take my my standard naming convention, and we are going to be able to create a shape, create a data structure which represents the shape of the camera. So the two things that are going to be needed to define a camera frustum are going to be the view matrix and the projection matrix of the camera. The view matrix defines where the camera is in the world and what it's looking at, and well, that's really mainly it. The projection matrix defines the shape of the camera, so that's going to be things like the field of view, the aspect ratio, and the near and far clipping planes. I'm not going to get all that much into what exactly the numbers inside the view and projection matrix are. Very briefly, the view matrix is generally defined by a to and a from position of the camera, as well as an up vector. And from there, you can construct everything else that you need. You can also think of it as the inverse of the world matrix, which represents the camera's position in space. In particular, the upper left 3x3 of the 4x4 view matrix is going to represent the camera's orientation in space. Let's pass a view matrix and a projection matrix to this camera constructor. These are going to be... I went back and forth when I was planning this out on whether I wanted these to be just the regular array of 16 values matrices that GameMaker uses, or whether I want these to be an instance of a slightly higher level matrix 4 class that I've been using for other things in the series, and I've decided eventually that I'm going to be doing the latter. I've made it fairly easy to convert between those two systems anyway. So, the first thing that we're going to do is I'm going to multiply the view matrix by the projection matrix, and this is going to essentially combine these two transformations from world space to view space, and from view space into normalized device space together, because we need both the position and the shape of the camera to be able to define the frustum. Next, I'm going to... So the first thing that I'm going to do is I'm going to pull out the values in each of the columns in the combined view projection matrix, and we're going to save them to variables independently. We're going to be doing a fair amount of manipulating those values in order to construct our frustum. So first, I'm going to save our C1. It's going to be a new vector 3, and this is going to represent the top 3 values in the leftmost column in the combined view projection matrix. And since I have essentially set up matrices to be a vector 4 or vector 4s, to do that I can say vp.x.x, vp.x.y, vp.x.z. And I'm going to do this with all of the other 4 columns in our combined view projection matrix. So column 2 is going to be yx, yy, yz, and z and w are going to be the last 2. Quick sanity check, did I do that right? It looks like I did, and we can move on. So from here, we can do a little bit of vector arithmetic, and we can construct 6 planes, which are going to represent the top, bottom, left, right, and near, far faces of our camera frustum. I'll start with left. I'm going to say the camera frustum's left plane is going to be a new call plane, and its normal vector is going to be c4.add c1, adding these two vector 3s, and its distance from the world origin is going to be vp.w.w, which is the last value in the matrix, so that's going to be the bottom right value in the matrix, and we're going to add that to vp.x.w. So we're going to add the last value in the view projection matrix to the last value in the first column. I'll probably have like a diagram or something of a 4x4 matrix on this side of the screen. That's not quite what I need to do to finish off the leftmost call plane of the camera frustum, but I'll get to what I have to do to finish this in a minute. The rightmost plane is going to be a lot like the leftmost plane, but instead of adding C1 to C4, we are going to subtract C1 from C4, and instead of adding these two values together, we're going to subtract them. And you may be starting to already realize a pattern emerging. We can have our bottom plane and our top plane. And that is going to be C4 add C2 and C4 sub C2. And for the distance to the world origin, we're going to add and subtract the last value in the second column from the left. And lastly, near and far. These can be C4 add C3, and we're going to add w.w to z.w and subtract those values for this one. Let's see, once again, sanity check, did I get that right? Alright, that looks good. So there's one more thing that I'm going to have to do to all of these planes, and that is going to be, in the same way that you can normalize a vector, you can normalize a plane. And normalizing a plane is going to be a lot like normalizing a vector, so we're going to ensure that its normal vector has a unit length of 1. And as opposed to simply normalizing that like immediately in the constructor, we're also going to adjust the distance from the world origin based on the magnitude of the normal vector. So let me go down to the bottom. I'm going to say normalize is going to be a function, and I'm going to have this return a new call plane instead of adjusting the values in the existing one. Let's say var mag is going to be self.normal.magnitude, and we can return a new call plane, and its normal vector is going to be self.normal.divide by the magnitude, essentially normalize the normal vector. That's not going to sound like a word anymore by the time I'm done here. And the distance from the origin can be self.distance divided by the magnitude. And that's going to be our plane normalization. And we are going to need to normalize these 6 planes before I proceed. And before we proceed, I also really should be committing these changes to source control. Let me do the plane additions separately, and let me do the camera frustum additions separately. Okay, have fun. So next, I'm going to want to write a method that's going to return the 8 corner positions of the frustum. So the 4 corners in the front and the 4 corners in the back. Technically, this isn't something that's really going to actually be used in frustum culling itself, but it's going to be rather useful for the debug draw and sometimes for other things, so I do want to include it. So this is going to be a getCorners method. This is going to return an array of 8 values representing the 4 corners, the 8 corners rather, of the frustum. And to actually figure out where those corners are, we're going to need to be able to compute the intersection points between a couple of these planes. So the intersection point between, for example, the back plane, the top plane, and the left plane, the back plane, the top plane, and the right plane, and so on and so forth. And doing that, there's both an easy way and a hard way, or at least a way that involves more code and less code. I'm going to define a method here. Do I want it to be a method, or do I want it to be just a standalone function? Because this isn't really like a method that belongs to the camera frustum as much as it's just a bit of code that's going to compute the intersection between any 3 planes. I'm going to call it call3 3-plane intersection, and it's going to take parameters p1, p2, and p3 for 3 planes. So this is going to boil down to basically solving a system of equations, and we're going to find a point that is lying exactly on each of those 3 planes. It is possible for 3 planes to not ever have any intersections, such as if the 3 planes are parallel to each other. And it is also possible for 3 planes to have not just a single point of intersection, but a line. But when we're dealing with camera frustums, we're only ever going to have a single point that's an intersection. And that's nice because that means that instead of having to do a bunch of matrix math, I can just get away with doing a few cross products, a few dot products, and basically calling it a day. So first, let me take the cross product of the normals of each of these planes against each other. So I'm going to call this var, let's say p2x p3, and that's going to be p2.normal.cross p3.normal. And I'm also going to want to have each of the other three combinations of these three planes. So that's going to be p3xp1 and p1xp2. The values that we're going to be crossing against each other are going to be basically what you expect them to be. Next, I'm going to add these three cross products together, but I'm also going to want to multiply them by the negative distance of the plane that was not involved in the cross product. So I'm going to say var cross product sum is going to be equal to p2x p3 dot multiply by negative p1 dot distance. And I'm going to probably break this up over multiple lines because this is going to be a little long. I'm going to add that result to p3x p1 multiplied by negative p2 dot distance, and I'm going to add that lastly to probably, again, are noticing a pattern, p1x p2 dot multiplied by negative p3 dot distance. Am I missing any parentheses? I am. Unfortunately, I do not have a way to describe visually how what we're doing here, which comes to mind. Anyway, lastly, we're going to return the cross product sum, and we're going to return that vector 3 divided by p1.normal dot product against p2x p3. And this is going to return us a vector 3, which should give us the intersection point between these three planes. And it also shouldn't matter which order you put these three planes into the equation. Alright, so when we're going back to get corners over here, I can say return an array, and this array is going to contain 8 of these. Let's say the first corner can be self.near. I'll try and make this code a little bit lined up. Self.top and self.left. And we can do this with near top left, near top right, near bottom, lining up my code, near bottom left and near bottom right, and also with the far plane, and all 4 of these combinations here. This is basically every combination of planes in the frustum, not counting the ones that are opposite each other. And that should give us the get corners method. Again, in my case, this is only really going to be useful for the debug draw, but sometimes it can be nice to know where the corners of your frustum are. And speaking of the debug draw, that I'm actually just going to copy and paste, because this is just going to be a lot of writing out connecting vertices, and at least computing the intersection between 3 planes is mildly interesting arithmetic. I think it's safe to say that simply building a vertex buffer and submitting it as a line list, connecting all of these 8 points in interesting ways, that's really just going to be tedious. And as long as these vertices are in the right order, we should be able to see the frustum in space. So, okay, so let's actually get this drawing in the game. So I did make one other change to this project. I did take all of the actual drawing the 3D world code and dump it in its own function, and that just allows me to draw the scene through both the main camera and the bird's eye view camera without having to, run the draw event twice or anything dumb like that. This function is going to take the view matrix and the projection matrix for purposes of frustum culling, and also, I suppose, for the purposes of debug drawing the frustum. So, the view matrix and projection matrix at the moment are just going to be the results of like matrix build look at, matrix build projection perspective field of view, and those are going to be the GameMaker arrays of 16 values. If I want to turn those into my own matrix 4s, I can say new matrix 4 of call view mat and new matrix 4 call proj mat. Feather is not going to like that because Feather isn't aware that the constructor here will take both a single array or 16 individual values, and we can combine those together into a new call camera frustum composed of those two matrix objects. And I can say var frustum equals that. And from here, I can just call the debug draw method on it. And I'm just going to take a quick look over to make sure that like the vertex former is what I think it is. So position 3D, normal text coordinate color. I think this is consistent between both my test project and this actual like live version, position 3D, normal text coordinate color. I don't need that open twice. And do I actually care about drawing this with the shader? Not really. It's just lines. Default GameMaker shader should be fine with that. Okay. And then that's going to be cleared and then reconfigured every frame. So if I run the game now, we should be able to see some lines on the screen representing the camera frustum. You can't see it in, well, you can sort of see it in the main view, but it's going to be like a rectangle that's barely like around the side of the camera, because again, the camera frustum is going to be basically the bounds of what the camera can see. So from the point of view of the camera, the line list vertex buffer isn't really going to be anything of interest that you can actually see. But in the 3D, in the bird's eye view down there, we can see that like when I look up, we have the shape of our camera, and it's just going to be again a very fairly long pyramid. The top is going to be lopped off, but you can't really see that because it is so small in this view. If I were to move around, we can see that we have our pyramid swinging around in circles. If I were to move, and if I were to run off in, let's say, this direction, that frustum shape is going to move with us. That's pretty cool. So we know that our frustum shape is working correctly as intended, and we can now, or that it's been set up as intended anyway. And from here on out, we can use this to do some collision checks against the quadtree and octree hierarchies, and we can use that to eliminate parts of the world that don't need to be drawn in any particular frame when they're not in view. When it comes to visualizing this is extremely unimportant, but if your far clipping plane is far away, that can make the frustum rather long and make it rather difficult to like interpret with your eyes what you're looking at. So if you want a somewhat smaller frustum, you can bring in the near clipping plane, and that's obviously going to make it so that things that are relatively close will not actually be drawn, but that will make the frustum in the debug drawer down there quite a bit smaller, and this may make it a little bit easier to like interpret with your brain what you're actually looking at. So that's going to do it for me for today. Next time we'll be using this to fairly quickly eliminate parts of the collision world that aren't in front of the camera and prevent them from being rendered. And then after that, going to talk about micro optimizations, and then after that, I am never going to talk about 3D collisions ever again. Anyway, my name is Michael. I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the video description. I hope you all find this useful, and I will see you all later. Special thanks to Zenjamin, VitroV, Squarecrow, Syndra Larson, Manta Ray, GameMaker, Edward Holt, DJ Gibbles, and Army Armbuster for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.